Hello everyone, this lesson is going to be on acids and bases. It'll introduce you to some new information and hopefully some of the information you will recall from previous science classes. So acids and bases, important molecules and ions that we'll start off with here. Hydrogen, kind of unique. It can end up with a negative charge looking like this. That's called hydride. So normally hydrogen, well, it always has one proton. Starts off with one single electron as well, which would mean it's neutral. So if it picks up an extra electron, it has one more electron, that is this one here, the hydride. In the case of the one that's important to us, though, it is the hydrogen that has the positive charge. So in this case, there are no electrons. It has lost its only electron. All we're left with is a proton, which of course has a positive charge. And this one is referred to as a proton because there is no electron, that is only the proton in the nucleus. So just realize here that when I do talk about a proton from now on, I'm not talking about the subatomic particle in the nucleus. I am actually talking about this positively charged ion of hydrogen. So that, as we'll see, is very important. In fact, it leads to the formation of this one here, which is hydronium. So you might kind of notice that it, well, sort of looks like H2O, water, only, well, we have an extra hydrogen and we have a positive charge. So yeah, if we take the proton that we were talking about previously, and if it's added to the water, well, this is what we end up with is the hydronium ion. That's going to be very important for acids. The next one here, important for bases, is the hydroxide. So you may recognize this from the table of polyatomic ions. This is the hydroxide ion. And the last one, water, written in maybe a different form than what you've seen in the past. Formally, of course, you would have seen it in this form here, H2O. But for many purposes, it's easier and better to write it as HOH. And even if you think of the structure of water, we do have the hydrogen, kind of on an angle anyway, sandwiched between the two hydrogen. And so that is our HOH, or water. So we'll kind of see why it's easier in some cases when we talk about acid and base chemistry to write it as HOH rather than as H2O. For Science 30, what we use are the Bronsted Lowry definitions of acids and bases. So there are various different definitions, but it is the Bronsted Lowry definition that we do go with for Science 30. So what does the Bronsted Lowry definition of an acid say? Well, it says that acids will donate protons, or they will give up their protons. So when they give up their protons, what they're giving them up to is water. And as we just saw, if water picks up the proton, then it just forms hydronium ion, and that's going to be on the product side. Whenever you have more hydronium that's forming, that is what leads to an acidic solution. The more acidic a solution is, the more hydronium ions there are, and that's what's making it more acidic. And of course, acidic solutions have lower pH values, a pH lower than 7. The more hydronium, the lower that pH value is going to be. Bronsted Lowry definition of a base is bases will accept protons. So acids donate protons, bases accept or they gain the protons. So if we have a base that's gaining the protons, typically where it's gaining it from is water. So if we take water and now strip a proton away, what we're left with is this here on the product side. The more hydroxide ion that you have, the more basic the solution is going to be. And exactly the opposite with hydronium. Instead of lowering the pH, it's going to increase the pH. The more hydroxide, the lower the pH. The more hydronium, the lower the pH. The more hydroxide, the higher the pH is going to be. Let's take a look at a few examples of reactions here. So in the first example are two reactants that we have. So a couple of things to go by to determine if something is going to be an acid. First of all, there has to be a hydrogen. There has to be a hydrogen because acids, again, are proton donors. If we take a look at our two reactants, We have hydrogen here, and we have hydrogen here. So both of these could be acting as an acid. And you might say, wait a minute, this is water. Water can't be an acid. Well, it actually can, according to the Bronsted Lowry definition, depending upon what it is reacting with and depending upon whether it donates or accepts electrons. So how is water behaving in this case? Well, if we take a look at the product side, we see Cl minus, which, well, kind of looks like this HCl, only it's missing the hydrogen. In fact, not only is it missing the hydrogen, it's missing a hydrogen and a positive charge. So we have taken away a hydrogen and a positive charge from HCl. And if we take a look at the other product, well, it's the water that has picked up that proton. So we have a proton that's being donated from HCl to the water. Proton donor is your acid, and in fact, this is hydrochloric acid, HCl. And the water is going to be acting as a base because it is accepting the proton. So in this case here, because we do have hydronium ions that are forming, what we're going to get is it's going to become an acidic solution, and we're going to see a decrease in pH. Something else to go by, so if it is an acid, there has to be the hydrogen, and also there will be AQ. So whenever it is an acid, it will have the subscript AQ, but don't just go by that because we see this one down here that's also AQ, but this one is not going to be an acid. So you need to look for a little bit more. It needs to have the AQ, it needs to have a hydrogen, and you may need to look at some other things as well, like is the hydronium being formed. The next reaction that we have here, we once again have water. And I'm just going to write this a different way now. I'm going to write it as the HOH, just to show it a little bit differently. And this one here, you'll find all of this on the table of polyatomic ions. What's going to happen with this reaction is very similar to what's happening at the top, only now we do have this one that is AQ. We do have a hydrogen, but the hydrogen's not in front. This here is a special kind of acid. If you see this COOH, this is what we call an organic acid or a carboxylic acid. Sometimes it's written like this. The carboxylic acid, oops, this should be an OH that we have right here. And what's going to happen is it's going to be this hydrogen right here that's going to be donated over to the water. So if we add the hydrogen with the charge, the proton, taking it from this one, that means that this is going to be the acid, and water, once again, is going to be accepting the proton, so it's going to be the base. So what do we end up with on the right-hand side? We get all of this benzoic acid without the proton, which is benzoate. And again, you can find this on your table of polyatomic ions. What we also have is our water, which picked up the extra proton. So we have the hydronium. So once again, because we're forming hydronium ions, this is also going to be an acidic solution that we do have, and it's going to lower the pH. We'll talk about this in another lesson, but there is in fact a difference between these reactions. So in the case of the first one, hydrochloric acid is what we call a strong acid. Every single one, 100% of these protons here in the HCl, they are completely stripped away from the chloride and they're donated to the water in order to form a whole bunch of hydronium ions. So we get really a big drop in the pH. In the case of the benzoic acid down here, for this one, we do have the protons that are donated to form the hydronium, but some are actually donated back as well. So there's a little bit of an equilibrium that is formed. So we do have the reaction that's going to the right, but we also have the reaction that's going back in the opposite direction to the left. So what that means is that because this reaction can reverse itself, we can say that, well, now the hydronium is donating a proton. So it is actually also acting as an acid, and the benzoate is acting as a base. In this case, because they're going in the opposite direction, we call them the conjugate. I'll just put C for conjugate acid, and the conjugate base on the other side, it's just the straight acid and base. Going on to the third example here, So here we have NaOH and AQ indicated for both of them. These are not acids though. So a big clue here, whenever you have a metal, in this case, it's sodium, but it could also be magnesium, it could be potassium, it could be barium attached to the OH. That is a pretty good clue that this is a base, and it in fact is a base, which means that the other reactant is going to be an acid. So up above, we saw that water in both cases was acting as a base. Now it's going to be acting as an acid. So what's going to happen? Well, it's going to donate its proton. In fact, when you take this NaOH, it is also an ionic compound. So when you dissolve it in water, this is what happens first, is the ions simply split apart. So we get Na plus dissolved in solution, hydroxide dissolved in our solution, which is the H2O. So why do we now talk about the donation of protons? Because in reality, what we're going to have is protons from here that are being donated over. It turns out being exactly the same, Na plus, and this is now our H2O here, and this is our OH minus. So it doesn't change anything in terms of what I previously wrote, but it does just show that because we have the water that's donating the protons, that's what makes it the acid. Here, though, we're not forming hydronium, we're forming OH, which means now, instead of having a drop in pH, we're going to have an increase in pH, which means that this is a basic or an alkaline solution. The last reaction here, again, we already know that this one here is a base. And we already know from the first reaction that this one here is an acid. So sodium hydroxide reacting with hydrochloric acid. We know then that this one is going to be donating the proton. It's going to be donating it, well, somewhere over here. But when we do have these solutions in water, again, first of all, if I just rewrite this, just like I did up above, and then if I write the HCl, now we can see a little bit more clearly that we have the HCl that's being donated over here. So what we end up with is Na plus in water, along with Cl minus dissolved in the water. We don't have any hydronium, we don't have any OH. In other words, there's nothing to cause this solution to be acidic, there's nothing to cause this solution to be basic, so what we end up with is something that has a pH of 7, and this is a special kind of reaction that is called a neutralization reaction. So we do have an acid, we do have a base, but they're kind of canceling each other out and resulting in the pH being neutral, having a pH of 7. The pH scale, you've all seen the pH scale before. I'll show you several different versions of the pH scale. So this is a fairly simple and straightforward one. It shows the range from a pH of 0, very acidic, going up to a pH of 14. Here it has alkaline. It doesn't matter if we call it alkaline or basic, though. We treat it as the same thing. Right in the middle, of course, pH of 7, that is neutral. So that would be distilled water. Okay, not just any water, not river water, tap water, ocean water, but distilled water that has H2O molecules and nothing else, that has a pH of 7. As you go lower, it becomes more and more and more acidic. The further you go with the lower numbers, to the left in this case, the more acidic. The further you go to the right with the bigger numbers, the more basic it is going to be. And I should also point out that this scale can extend beyond 14. That would be what we call a super base, and it can in fact go into negative values like -2, and those are what are referred to as super acids. But for the most part, we just talk about the basic range, which is from 0 to 14. So let's bump it up a little bit and talk about more Science 30 stuff. So this one's kind of nice. It shows the same arrangement going from the low pH values on the left to the upper pH values on the right. Again, the scale is 0 to 14, 0 right in the middle being neutral. And it also has a number of different examples here, samples of different fluids and what their pHs are. So your body fluids, blood, slightly basic, very close to neutral, but ever so slightly basic, a pH of 7.4. If we take a look at something like vinegar that you might put on your French fries, usual pH is typically somewhere around 3 for vinegar, Stomach acid, considerably more acidic, a pH of around 1. Here it has 1 to 3, but it's usually fairly low and fairly acidic. In your house, baking soda, pH about 8.5. Cleaning solutions that contain ammonia, pH around 11 or 12, so quite basic for those. But this pH scale shows something else that's really important for Science 30, and that is this right here, hydronium ion, and the square brackets means concentration. The concentration of hydronium ions, and the units for concentration are moles per liter. So all of these numbers here, 10 to the negative 2, 10 to the negative 4, 10 to the negative 7, those are all of the concentrations in moles per liter. So let's start with our neutral solution. 10 to the negative 7, what does that really mean? Whenever you have an exponent and it's negative, that's a small number. It's a very small number. If it's negative, the bigger this number is, the smaller the number is going to be. So this number here is actually equal to 0.0000001. So how does this turn into 10 to the negative 7? Well, initially the decimal is here, and it's moved over 1, 2, 3, 4, 5, 6, 7 places to the right, and that's where we get the 7 from. It's negative because it's a really, really small number. So if we had a big number, like 10 to the 4, now the decimal is in the opposite direction. So now we would move it over 1, 2, 3, 4 places. And this is actually 10,000. Okay, so we're talking about really, really small numbers in terms of the concentration. So if we were to take a look at this one here, 10 to the negative 4, this one here is the same as 0.0001. Again, we move the decimal over 1, 2, 3, 4 places. It's a small number, so it's the negative. Now let's compare this number here to this number here. This one here is actually much, much smaller, and this one here is bigger. So as you go away from the neutral solution to more acidic solutions, you get a bigger concentration of hydronium ions. And again, that was one of the definitions of an acid, is it does produce and increase the amount of hydronium ions. As we go further and further away in the opposite direction, we get fewer and fewer of the hydronium ions. We get smaller and smaller numbers for the concentration, and that means a less acidic or a more basic solution. Just as a little bit of an aside, I did mention the hydroxide ions as well. We don't have it on this picture, and it's not so much Science 30, but as we go to the right-hand side here, more basic, there would be fewer hydronium, but there would be more hydroxide. And way over here, there would be more hydronium, but there would be fewer of the hydroxide. So kind of an inverse relationship between the amount of hydronium increasing the acidity and the amount of hydroxide ions. One more picture of the pH scale, and notice that the orientation on this one is different, so pay careful attention to that. So here it does have acidic solutions at the top, and again some examples of them. Neutral pH right in the middle here, and our basic or alkaline solutions down at the bottom. It's using this legend here to show the, well, here it just has the protons, but in reality it should be the H3O plus that they are talking about. So as we do go to more acidic solutions, we have more of these red spheres, so this would be an acidic solution. As we go to more basic solutions, we have more and more of the hydroxide, which are the blue circles or spheres according to this diagram. So the other really important thing is on the left-hand side, and again here they're saying the hydrogen ion concentration or the proton concentration, but once again it really is the hydronium ion concentration. So what this does show is what is referred to as a logarithmic scale. The pH scale is a log scale, and this is what the picture is showing. As we go from a pH of 7 to a pH of 6, it's a change of only 1 pH value, but it's 10 times more acidic. If we take a look at lemon juice, which has a pH of 2, compared to distilled water, for each change of 1 pH value, it is 10 times more acidic. So 10, 100, 1,000, 10,000. Lemon juice is 100 times more acidic than distilled water. Same pattern as we go in the opposite direction. So if we take a look at ammonia here, we're going 10, 100, 1,000, 10,000. So ammonia is 10,000 times more basic now, 10,000 times more basic than distilled water, or 1/10,000th as acidic as distilled water. Okay, that is the logarithmic scale. And in the future lesson, we'll be doing some calculations using the log scale to calculate hydronium ion concentrations and the pH of solutions. Just one final slide, and this is one thing that hopefully is a review for you, the properties of acids and bases. So both acids and bases, when they do dissolve in water, they do form ions. So if we take a look at hydrochloric acid, HCl, fairly common acid, when we take it and we dissolve it in water, even though protons are donated, let's just write it down as this for now, there are protons formed, there are chloride ions formed. Whenever there are charges that are formed, it's going to conduct electricity. Same thing with NaCl, or sorry, we'll do NaOH for a base. Dissolve it and we get sodium ion, we get the hydroxide ion. Again, the key is there are charges, so they will conduct electricity. Litmus, there is red litmus paper and there is blue litmus paper. So if we use blue litmus paper and put an acid on it, it will turn red in color. If we take a base, it turns red litmus blue in color. Okay, what about if you use red litmus for acid? Well, it just stays red, and blue litmus stays blue when it's a base. So the key really is think red for acid, whether it's red or blue litmus, and think blue for a base. In the case of acids as well, they do react with active metals. So usually one of the metals that we talk about is magnesium. If you put a magnesium strip, a little piece of metal, into an acid like hydrochloric acid, a strong acid, then there is a gas produced, and that is hydrogen gas. So that's a property of acids. Bases, slippery to the feel, typically. Acids taste sour. Again, think about common ones. Like fruit juices and lemon juice and lime juice, citrus fruits, they contain citric acid. Vinegar is acetic acid. For bases, the opposite. Instead of tasting sour, they taste bitter. We saw a neutralization reaction. So something like hydrochloric acid will neutralize a base, like sodium hydroxide, through that neutralization reaction that we saw. And in both cases, they can be corrosive.